Welcome back. This is video 11B. We're going to continue with probability and look at some examples of what's called a probability distribution. So one way that to describe a probability distribution is to list every outcome when you have some experiment along with each outcome's associated probability. So when you have that, each outcome and its associated probability, that's called a probability distribution. So we're going to look at two examples of these today. So the first one comes back to this example that you saw in video A, where in Math 127 we have 24 students in class. We're going to look at the probability distribution for the number of students who show up on any given day. So if you can imagine, if there are 24 seats, all the possible outcomes would be perfect attendance, one person absent with 23 students present, 22 students in attendance, 21 in attendance, and so on. When we look at this probability distribution, this was made by simply subjective probabilities. We did not base this on data. So here you have this in your notes. And so if you see the number of students that are present, it could be that everyone's present. It could be 23 students are present, 22 students are present, and so on. Once we got down to 15 or fewer students being present, I hope the likelihood of like 5 or 3 students being present out of a class of 24 is fairly small. We did lump those together, 15 through 0. And then below each one of these, you'll see the corresponding probability. So this says the likelihood, the probability of 24 students being in attendance on any given day is 0.10 or 10%. The likelihood of 23 students being present would be 0.2 or 20%. Okay, so we have some questions with this. Give the probability that 1 or 2 students are absent. Now remember, this is number of students up here that are present. And we're asking about 1 or 2 that are absent. I found that with probability, the probability part's not that hard. Sometimes students get tripped up with the wording of the problem, so watch the wording and that you understand what the words mean. We want the probability that 1 or 2 are absent. Since this is written in terms of how many are present, if 1 student's absent, that would mean that 23 students are present. And if 2 students are absent, that would mean that 22 students are present. So this is the same thing as looking for the likelihood that 23 or 22 students are present. And those probabilities are given, so we just simply need to take those 2 probabilities and we'll add them together. And so we estimate there to be a 0.40 probability, or as a percentage, a 40% probability that we have 1 or 2 students absent on any given day. Okay, next question. And again, we'll be very careful with the wording here. What's the probability, still a probability question, that at most 1 student is absent? At most 1. Okay. Again, watch the wording, and there'll be all different kinds of wording. We can't possibly go over an example of every single kind of problem. It might be at most 1, at least 1, no more than 1. So at most 1, that means no more than 1, right? At most 1. It could mean that 0 are absent or 1 are absent. So this means 0 or 1. Might want to, I know I wrote that kind of small, but write yourself a little note. That means 0 or 1 could be absent if it's at most 1. And then recall again that your table is in terms of the number that are present. And so if 0 are absent, that would be perfect attendance, 24 are in attendance. If 1's absent, that would be 23 are present. So we're really looking for the likelihood that 24 or 23 are present. And again, we have those 2 probabilities, so we're just going to sum those up. So we get a probability of 0.03 or a 30% chance that on any given class we have at most one student that's absent. All right, let's go to part C. All right, part C. What's the probability that at least 4 students are absent? So at least 4 students are absent. Again, make sure that you know what at least 4 is. I'm not sure why, but sometimes at least students get confused and they want to make it like less than 4 students. I always tell everybody you're going to an amusement park, you have to be at least this tall to go on the ride. That means you better be that tall or taller. So at least 4 means 4 or more. And I know that sounds silly, but that's why people get these probability questions wrong, is interpreting the words, not the actual math part. So at least 4 absent means it could be 4 are absent, 5 are absent, 6 are absent, all the way up to, heaven forbid, everybody being absent, right? Again, our table is written in terms of the number of students that are present, and so if 4 students are absent in a class of 24, that would mean that 20 students are present. If 5 students are absent, 19 students are present, and so on. If we had 24 students that were absent, nobody would be present. So this is what we're looking for here this time. And so the probability that at least 4 are absent, we could get by summing up all these probabilities. The probability that 20 are present, 19 are present, 18 are present, all the way down to 15 through 0 being present. So if we sum those up, and if we sum up those probabilities, they should sum up to 0.35. Or a 35% chance that at least 4 are absent, meaning 4 or more. All right, I think this problem has one more part. All right, part D. What is the sum of all the simple probabilities for this probability distribution? These are the simple probabilities. And if we were to sum all those up, what do they sum up to? Well, I might not write all these here, but if you sum up all these probabilities in your probability distribution, what happens here is not a coincidence. This should happen for any probability problem. If you've listed all the possible outcomes and there's nothing else that could happen, the probability should sum up to 1. And so they do in this case. So if you sum all those up, they add up to 1. If you write that as a percentage, that would be 100%. Should sort of make sense. These are the only possibilities in a class with 24 seats. The only possible things that could happen is that you have 24 students present, 23, all the way down to no one here. So this is not a coincidence, and we'll, in a future lesson, write down this rule that the sum of all probabilities will always be 1. All right, let's move on to a second probability distribution problem. All right, so in the second one, we're going to approach this one a little differently. The first one we had a table. With this one, we're going to give a mathematical function and associate the area under a curve with the probability of certain outcomes. So let's say that you take a train home from work every day. The train arrives. So, okay, you work in New York City. Sorry, I had to refresh my memory about the problem. The train arrives like clockwork every 10 minutes at the stop that you take the train at. The time that you get to the platform each day is more or less completely random because you leave work at different times each day. So you're not really sure when you get to the train station how long you're going to wait, but you know that they come every 10 minutes. You could get lucky and wait 10 seconds, or you might have to wait the full 10 minutes. There goes the last train. So your wait time for the train can be described by what's called a uniform probability distribution, because every imaginable wait time is equally likely. You're equally likely to wait 1 to 2 minutes as you are 9 to 10 minutes. Okay, so you take this train home from work each day. What's the shortest and the longest periods that you could wait for the train? Well, since it's coming every 10 minutes, you could get really lucky. You could walk right up and walk right onto the train, so the shortest time would be 0 minutes. The train's there waiting for you. Or you could run up those stairs to catch the train, and there goes the train. Doors just closed and I pulled away, so you're going to have to wait a full 10 minutes. And so as long as that train is like clockwork there every 10 minutes, you're going to wait somewhere between 0 and 10 minutes, those being the extremes. Okay, how about on average? How long are you going to wait? If those are the extremes and you're equally likely to wait any time within that range, it sort of makes sense that the average is going to be the value right in the middle of those, which would be 5 minutes. For a uniform distribution, it turns out that a uniform distribution that has what are called endpoints of A and B, our endpoints are 0 minutes and 10 minutes, that the average is always going to be the number right in the middle of those. So it will be true for anything that follows a uniform distribution. That the average time will be the value right in between those endpoints. So it sort of makes sense. That's works for the one that we just looked at. If you're going to wait somewhere between 0 and 10 minutes, if we take the average of 0 and 10 minutes, your average wait time is 5 minutes. So this will always be true when you have a uniform distribution. All right, we can also draw a picture of what the uniform distribution looks like, so we'll do that with part C. So draw a picture, draw a graph of this probability model. Okay, if I let my variable be down here on x, so let's say x here is wait times for the train, and they're in minutes. I know I'm going to wait anywhere between 0 and a maximum of 10 minutes. These are those endpoints A and B that we talked about a second ago. The height of this graph is going to represent the probability, the likelihood of certain times. So this is going to represent the probability. Since I'm equally likely to wait any one of these times within this range of values, I'm going to draw a rectangle. The likelihood here is not going to change. It'll be the same from 0 to 2 minutes as it is from 8 to 10 minutes, let's say. And now I need to figure out what the height of this rectangle should be. When we look at a probability model with a graph, the area under the graph represents the probability. And we just talked about how the sum of all the probabilities had to be 1. And so we want the area of this rectangle to be 1. And to get the area of that rectangle to be 1, length times width has to be 1. So from here to here, this has a length of 10. We need 10 times something that's going to give us 1. So the something would be 1/10. This will always be 1 over b minus a. If you take whatever the length of your rectangle is, the width of that must be the reciprocal of that length there. So just to write down a few things I just said, we have to have a total probability of 1, and so the area of that rectangle has to be 1. That area represents the total probability. And so that's how we got the height of 1/10. And now that we have our picture, now we can use this to compute certain probabilities. So if we want to figure out the probability we wait, more than 3 minutes or less than 3 minutes or whatever happens to be in questions D and E, we can figure that out. So let's move on to those. All right, 2 minutes. So what's the probability that we wait less than 2 minutes for a train? I can almost keep a lot of this up here. Draw and shade the graph. So here's my probability distribution. I want to wait less than 2 minutes. Now be careful. When we had the number of students being absent, if it was like less than 2 students are absent, that would mean 1 or 0 are absent because that was a discrete variable. Less than 2 in this case, this is something that's continuous. You can wait less than 2 minutes for the train. Doesn't mean that you wait 0 or 1 minute. You might wait 1.5 minutes. And you're waiting less than 2 minutes. So we'll draw in where 2 minutes is here. And we can be anywhere less than 2 minutes. So I'm going to shade here. We can wait 1.999 minutes and we waited less than 2 minutes. If I find the area of that rectangle, that area corresponds to the probability. So if I want to know the probability that we wait less than 2 minutes, that is the area under the rectangle from 0 to 2. And so hopefully you remember how to find the area of a rectangle, length times width. And so if we look from here to here, that has a distance of 2. If they were different numbers, you'd just be looking at the difference of those. And then the height of that rectangle is 1/10. So we'll end up with 2 over 10 or 1/5 or 0.20 or a 20% chance that you're going to wait less than 2 minutes for the train. All right, and then we can do some similar problems here with different times. So let's look at a couple more in E and F. So in E, what's the probability that we wait at least 6.5 minutes for the train? I'll adjust my picture. And again, watch the wording. Make sure you know what at least means. So 6.5, here's about a half. 6.5 is about up here. Think about where you should shade. I waited at least 6.5 minutes. That means I waited that amount of time or more. So I'm going to be shading here. And so that's going to be the area there of my shaded rectangle, the area from 6.5 minutes to 10 minutes. And again, it's just length times width. The distance here from 6.5 to 10, we just subtract those two. So 10 minus 6.5, that has a length of 3.5. We'll multiply that by the width of that rectangle is 1/10, so we'll get 3.5 over 10. Or as a decimal, 0.35, or as a percentage, 35%. That's that one. We'll do one more with this one. A little bit of a different question in part F. Draw, label, and interpret the 90th percentile for this probability distribution. All right, in the two previous problems, we were looking for the probability. 90th percentile, this time you're kind of given a probability. We're going to try to figure out what wait time corresponds with that. If we think about the mean was 5 minutes, this is a percentile, right? This is the 50th percentile. 50% of the time we wait less than that amount of time. 50% of the time we wait more than that amount of time. We want to know about the 90th percentile. 90% of the time we wait how long or less. So it's not going to be here. This is the 50th percentile. It's got to be somewhere up here. And you can kind of look at this one and figure this out, but let's pretend this is a little bit more difficult because the numbers won't always be so easy. This way you can say, oh, does my intuition match my answer? But this area right here, 90% of the time we're going to wait this many minutes or less. I know you can probably look at that and know the answer, but again, sometimes the numbers won't always be this convenient. So we're going to use the fact that that area, again, can be found by using the length times the width of the rectangle. You know that's 9, right? But if you didn't, if the numbers were more complicated, you could say, hey, that area is 0.90. I don't know how far it is from here to here. So that length is x minus 0, and I do know the width of this thing. And then if you solve this for x, this is just going to be x. Multiply both sides by 10. We'll get what we thought we were supposed to get, 9 minutes. So 90% of the time, you're going to wait 9 minutes or less. 10% of the time, you would wait 9 minutes or more. All right, and that's it for examples of probability distributions.